Well, here we are again. And first thing, I have to take my glasses off so that I can better see the screen. And I have to forget about the camera, and then I can get my hair a little bit back. I think. Oh, it's all over the place. If I forget the camera, then I can coordinate with my hands. Okay. So, and if I look straight into the camera, you can see my eyes. And if I look to the bottom of the screen, you get a squinty-eyed guy with eyes closed. Well, anyway, I'll try to do it right. Oh, now I can't see the screen because I look in the camera. Well, and then the other thing I have to do is to turn on the pointer. It's becoming a checklist nearly. Okay, and at the last presentation, which was a while ago, we explained igneous rocks and how they're being classified. And now we're moving on. And although we didn't quite finish the igneous rock classification, so we're doing that in this presentation, and then we move on and look at volcanic rocks, and then a little workshop or an attempt to a virtual workshop where we're going to classify or try to classify rocks. And now that way you get confronted a little bit with the realities of geology. So we left off here with the classification of plutonic rocks, rocks that form in a magma chamber and cool off and never see the surface, as opposed to volcanic rocks, which is magma that reaches the surface and flows out from there, either on the ocean floor or on the continent. But plutonic rocks, so magma chambers and plutons that are embedded within the crust, they were classified two ways. One way is based on crystallinity, the size of the crystals, and the distribution of crystal sizes. And the size of the crystals, if the crystallinity, the crystals are large, relatively coarse, and you can see them in your rock sample. If lucky, even with bare naked eyes, then we call them phaneritic. And if they're all very fine-grained, and we can't see really much in the bloody rock, then we call them aphanitic. So when you apply a rock classification based on mineralogy, then they need to have coarse enough crystals to see them and to identify what rock minerals they are, right? And that is the second part of the classification, based on mineral composition. Okay, so we need at least relatively coarse-grained materials, phaneritic. And then the second is when we look here on the right, where we do the mineral classification of the rocks that we're dealing with, then we're dealing only with light-colored minerals like quartz, alkali feldspar, plagioclase, and the anti-quartz phoids. Phoids or feldspatoids and quartz occurrences in rock are mutually exclusive. So if I have quartz, there is 0 phoids, and if I have phoids in a rock, then I have 0 quartz. Okay, and these are all felsic or light-colored minerals, and if there isn't enough in them, I cannot classify the rocks. So I need at least 10% of felsic minerals, quartz, alkali feldspar, plagioclase, and phoids. And then if there's quartz, there cannot be any phoid, and if there's phoids, there cannot be any quartz. Right? And that's why we have these two ternary diagrams that basically form a diamond together. And a ternary diagram means that at the corners, at the corner angles there, that is where the mineral is maximal. So we have here the quartz corner, and we have here 90 to 100% quartz. And if you had a rock that was composed 90 to 100% of quartz, and you have to watch out there, because the felsic content can be as low as 10%, right? So then you have 100% of 10% is 10% quartz that make up the rock. And the rest of the rock can be entirely mafic, can be entirely composed of dark minerals, right? But we still call it a quartzolite because 100% of the light content, the acidic or felsic content, right, all names for the same, is composed of quartz. And then you have a quartzolite anyway. If I have 0% quartz, which is the scale here at the bottom of the triangle, that's 0% quartz, right? Then, and I have a lot of plagioclase, I can have an anorthosite or a gabbro, right? Usually gabbros are very low in quartz, and therefore they are very dark colored in rock type. They're mostly dark minerals there. Okay, if I go to the bottom ternary diagram, I have the same, but now with voids. So there is no quartz, 0 quartz, yeah? And then you can also have 0 voids. Then you're at the base of this downward pointing triangle, right? And then on the left you have alkali feldspar angle, so that's 100% alkali feldspar. And then on the opposing triangle side, and the opposing side, that is 0 alkali feldspar. And here at this corner you have 100% plagioclase, and on the south there we have the voids, and on the upper part there we have the quartz rich quartz containing rocks. And so here we have 100% plagioclase, and there on this side of the triangle, or on this side of the triangle when dealing with voids, we have 0% plagioclase. So the composition of quartz plus alkali feldspar plus plagioclase plus void represents 100% of the light mineral content, right? And so now you can kind of, let's see whether this works. I have an animation, there it is. So now you can determine the composition based on, here in the upper triangle, based on quartz content. Say I have 50% quartz, so we go between 0 and 100% quartz, halfway there, that is the 50% line parallel to the base of the opposing side. Right. 0 to 100, halfway is 50%. Then we can say, okay, I got alkali feldspars in my rock. I can see those under the microscope typically. And this is 0 alkali feldspar, and that is 100% alkali feldspar. I see about 30%. So there on the intersect, that is where I have my rock composition. All right, granite. This is in the granite field. And I know how much plagioclase I have, because quartz plus alkali feldspar plus plagioclase equals 100%. Alkalis are 30%, the quartzes are 50%, so the remainder is 20% of the plagioclase. So that would be, this would be the parallel 20% line, parallel to the base of the 0 plagioclase side of the triangle. Now, this is as good as I can tell it to you. Okay. So you need 10% light minerals. You need a phaneritic rock so that you have large enough crystals to see what the composition is, at least under a microscope. Right. And then of those minerals, you need 10% at least of light or felsic or acidic minerals. Quartz, alkali feldspar, plagioclase, and voids. And quartz and voids are mutually exclusive. And then based on the normalized composition, then you can plot what the rock type is. Okay. So if you have a rock that has 10% or less, right, then typically you, according to, or around 10%, if you have plagioclase, we call those the gabbroid rocks. And the light content can be void or quartz, but it is 10% or a little bit higher, and it is dominated by plagioclase. You can see that here in the area. And now you have gabbros, and then within the gabbros, you can look at the dark mineralogy, the dark minerals, and you can say, are these pyroxenes or olivines? Right, that is the bulk of the dark minerals that you have. And if you normalize again, pyroxene, olivine plus plagioclase being 100%, then you can plot anywhere in this ternary diagram and classify. Oh, this is a pure gabbro here, right? On this side, with a lot of, with 0 olivine, or on this side 100% olivine. And here there is 0 plagioclase, and mostly pyroxene and olivine. So these are very dark minerals, and you see hardly any felsic material at this point. And then you go to this ultramafic triangle C, where you have olivines, and then you have orthopyroxenes and clinopyroxenes, and then based on the renormalized composition of these 3 endpoints, you can call them harburgites, olivine westerapsites, or websterite. And so this goes too far for me, and certainly for the current level of classifications. But you know that you have to refine your classifications based on composition by also classifying the dark content of the minerals using these 2 graphs. So here you have a piece of granite, and there is a lot of light minerals in it, right? That's the felsic content, and that composes of quartz, alkali feldspars, and plagioclases. And if you have about 40–50% quartz in here and 30% alkali feldspars, then it classifies as a granite. So here you see a granite. Same way, if you have still a high quartz content in the felsic light colored minerals, right, then you have to see where the alkali feldspars plot and the plagioclase. And if the alkali feldspars is less than 30% typically, so that plots in this field, then we have a granodiorite. That's how that looks. If the quartz content or the felsic content gets lower and a large portion of the rock composes out of dark minerals, then typically we're dealing with a gabbro. And 10% of the rock is then maybe or less is quartz or feldspatoroid. You can have gabbros on both triangles. And then if the white stuff is mostly plagioclase, then we call it a gabbro. If it is mostly alkali feldspar, it's a cyanide. And typically these are lighter in color. So gabbro or a diorite plots here in this corner, and this is an example of a diorite. And typically diorites have a lot of dark minerals as well, and the felsic content is relatively low and plagioclase dominant. Now here we are less than 10% felsic, and it's all dark minerals, and we look like we have a lot of pyroxenes in it, so we're in the bottom part of the diagram, and there's relatively little olivines in it. So this is an ultramafic rock because it's less than 10% felsic, and it is dominant in orthopyroxene, so then we get the Websterite light name that we were struggling with before, and that is how it looks like. So that's quite a range of rock. Now, if we have a phaneritic or a coarse crystalline rock, right, like this one, which has very large crystals, then it might be formed due to very slow cooling in a vein of the rock, a vein formed by a fracture or a fault, and then being filled up with slow cooling magma, and then we call that a pegmatite. So now we're going to go talk about volcanic rocks. Magma that float and reach the surface of the continent or the ocean floor. And here is an example. We get here a rifting zone. Remember the oceanic rifting zone here formed in the Red Sea and going through into Gulf of Aden? Well, it splits up, and then we get here the East African Rift Zone. You can have an eastern branch and a western branch, right? And these rifting zones going through continents tend to be more sour or felsic in nature, acidic. Right? And so we get here on this continent part, we get volcanoes. Like the Kilimanjaro in Tanzania. So you don't only get volcanoes along active subduction zones that we talked about, and that especially occur in the Pacific Ocean, where we get volcanoes along in Indonesia and other Polynesian islands, or along the Andes and the Rocky Mountains. Well, not the Rocky Mountains, but the west coast of Canada and Washington, where we have Mount St. Helens, right? That's where you get a lot of those active margin volcanoes, and this is a rifting zone volcano where the rift cuts through the continent and where the continents start to split and drift apart over millions of years. And there we have the Kilimanjaro as an example in Tanzania. And in Indonesia, we have the Tangkuban Perahu. And that is in the Indonesian language, and it's translated as the overturned boat, and it is near Bandung on the island of Java in Indonesia. And you can visit this. It's a nice tourist trip, and then you can walk through this still hot crater of the volcano with their geysers sticking up. And I was there about a decade or so ago, and I'll show you rock later on from there. But these volcanic rocks, they have their own phaneritic and aphanitic classifications, and they also have a compositional, a mineralogical classification. So you again need to have 10% light minerals, quartz, alkali feldspar, plagioclase, and or phoids, right? Phoids and quartz being mutually exclusive. So you can have a rock that is high in quartz, right, and has plagioclase in it and some alkali feldspars, and then it plots as a rhyolite. And then we have here not mineralogical but more textural ternary diagrams to help classify these rocks. And here we have volcanic glass, So that is super fast cooling. Obsidian is an example of that. And there you have rock fragments, which is often explosive materials blown into the air when the crater of the volcano or part of the volcano explodes. We get volcanic ash and rock fragments being spewed into the air. Or if we have lava flows and they crystallize out, right, then you can have crystals, right? And then here you can get one based on the parts, the size of the particles. So you can have pyroclastic rock. This is typically with ash particles less than 2 millimeters. If they are a little bit larger, like little pieces of gravel, say 2 to 64 millimeters, 6.4 centimeters, that's called lapilli. And if they're really blocks and bombs that were shot as fragments into the air, right, and then glued together, they're often called pyroclastic breccia if they're very angular in shape, and if they're rounded in shape and glued together, we call them agglomerates. Okay, so here you see a rock high in quartz content. We think it is. We could see under the lens that there was a fair bit of quartz in it, so we could classify how much quartz there was, and then the rest is probably plagioclase and alkali feldspar. So that would plot somewhere here in the rhyolite field. So we're looking here at a piece of rhyolite. There we are low in quartz, but we still have a lot of feldspar, alkali feldspars, and then it's a cyanide, right, which plots in here and there. And it depends a little bit on the classification, right? But this here it's called trachyte, but that is also known as a cyanide. And it can be a photoid or a quartzitic cyanide. And that's what you see an example of it. On this side of the volcanic rock spectrum, we have a lot of dark minerals. There are big gas bubbles in there, right? And it looks a little bit like cinder, right? And it's high in dark minerals, so and high in plagioclase, and this is an andesite basalt, right? And if it's light colored, it can be more andesitic, and it's often called, with lots of gas bubbles in there, and angular breccia fragments, right? Nearly lapilli sized, and that would be an andesitic porphyry. If you have this stuff here, it is basically very light in weight. It is basically the frost that comes along and cools off on the top of the lava flow, right? And it's called pumice. And because of all those gas bubbles, all these little pores there formed due to the escape of gas in the last when it cools up on top of the lava flow, that is what creates a very lightweight rock, and it's called pumice. And if it is high in plagioclase and dark minerals, it looks like this, and it's kind of in the same group as basalts, but because of the enormous amount of gas escape bubbles, it looks and classified as cinder or scoria. Again, like the pumice, it forms on top of the lava flow, but it's dark colored. Here you have a rock, right, with a lot of lithic or rock fragments, as you can see, all these square parts there and the brown parts there. right? So it is high in rock fragments, and it's not very vitreous. You cannot see through it. It's not indicative of very fast cooling, so it's not volcanic glass. And it's not crystalline. These are particles, fragments, so it is not a crystal tuff. This is a lithic tuff, and the tuff often has lots of those pumice-like pores in it as well. It's relatively light. And here is a big fragment that was shot into the air during the cooling process. It was kind of more rounded here, and we call that a volcanic bomb, and it is definitely larger than 6 centimeters. The thing was nearly a foot long. I saw this in real life. So now you have a little bit idea about how to classify the rocks, and I got some examples here with me as a mini workshop, right? And if you look at this rock, it is especially clear. You see many gas escape bubbles. And this piece of rock, along with this piece, I found in the crater of Tangu Lap Pau, the overturned boat. Sorry. And this is tough. I cannot see, if I look at the crystal size in here, even with the magnifying glass, I don't see here much in it. A few fragments of rock, but a lot of bubbles. And those concentric circles are probably weathered iron minerals, right? So it's probably rock fragments rich, so it would be a lithic tuff in our classification. Okay, so that is lithic tuff, fits there. Okay, on another trip, a decade ago or so, I saw this stuff. You see it? This is from Vietnam, near Phong Tao, which is a resort town along the, I think, the Indian Ocean, on the coast of Vietnam. And so this is another example of a plutonic rock. And as you can see, I can see it with my lens. I don't see a dam. This is very fine crystalline. And so from that point of view, it's aphanitic. It's an aphanitic plutonic rock probably. And so I can try to estimate how much quartz is in it. Well, it doesn't look very quartz rich. Maybe 10–15%. But it is a guess. But it is not super dark. It's maybe 5–10% mafic rocks, and the rest is feldspars, right? And then, because of its green color, this can contain weathered plagioclase, which weathers green, autoclases or alkali feldspars, weather typically reddish in color. And maybe the green color is due to mafic minerals that also tend to weather green, such as pyroxides. So really, I think that we're dealing with something like a quartz monzonite or a monzodiorite. And on this part of the double triangles, that we have a plagioclase dominant rock there, and if it is filled with phoids or with some quartz, it is referred to as gabbro. And then it's the composition of the black or the mafic minerals that help us decide what the what kind of a gabbro we're dealing with. Okay, we went over that a few minutes ago. So for my guess is we are somewhere here in the monzonite, monzodiorite area. But how would I really know it? Why? Because I'm bluffing myself through it, right? Because I can see it there. Geologists often tend to do that and don't fall for it. What I should do is take a slice of this rock and make it into a thin section. You see? I grind it down, polish it, and it gets so thin that you can see my face through it, or read a newspaper through it. It's about 30 angstroms in thickness, 30 microns in thickness, sorry. Mixing up my units. And then I can shine light through it, plain light, or polarized light, or through directions of polarized light, which we call cross Nichols, and that can then reveal the birefringent colors on the color spectrum of these minerals in here. And I can use the colors to identify what kind of a mineral I'm dealing with. I can also look at the crystallinity of the minerals. I can stain the minerals so that I can identify them with chemical stain as to what I'm dealing with. But I need a transmitting light microscope for doing that. So don't believe that for a minute that I could tell you what the real mineralogy in here was. I just was gambling. It's not that dark, right? Oh, I don't have a, but I can see the felsic components. Yeah. But if it is 10%, then maybe it's quartz or void. And that is how you can kind of BS yourself through it. But for really working with this, you need a thin section. A slice of rock 30 angstrom thick, mounted on a glass plate and protected by a little glass cover. So, we're getting close to the end of this presentation. And here you see some field outcrop. The geologists that describe this think it's about 1.8 billion year old. Lava layers. You can see the rock is layered here, like the bedding is going this way. And so it's not plutonic, it is layered, and the composition of it is a rhyolite. So these are rhyolitic lava layers from Mount Mingus in Jerome, Arizona. And realize that geologists are not the only bullshitters, because in Jerome we have what they claim to be the best hamburger joint in North America. No, no, no. I, as a true blue Alberta boy, immigrant, know where the best beef can be found. And it's in Alberta country, in Alberta beef country. So here are some more people that try to bullshit you. But these are 1.8 billion year rhyolite layers around Jerome in Arizona. And here nearby is another group of layers there. And they are very light in weight, and they are probably volcanic ash layers. And then here, this accumulation in the center is a spot where a number of volcanic bombs came and fell and then got embedded by more volcanic ash. So here's a close up. You see the bombs, they're big, they're large, much larger than 6.4 centimeters. Definitely not lapilli. Maybe this stuff has lapilli in it, but those are volcanic bombs. You can see how the later ash layers kind of draped around it, over it. So, some more. Here is a map with Mount Mingus marked there, and it is in what they call the transition zone in Arizona. There's Flagstaff, and this is the Colorado Plateau, and here we have the Basin and Range area with Tucson and Phoenix, right? And these are two structurally major continental plates that are moving over what we call a hot spot, and therefore you get a lot of volcanism here. And Mount Mangus, that started already 1.8 billion years ago. But there we have near Flagstaff another volcanic activity, the Sunset Crater, which is only 1100 years old. So this is a very interesting area structurally. So the Sunset Crater formed along a 6-mile fissure in the Colorado Plateau, that green stuff in the top of the map. And it's the largest of a series of smaller cinder cones. Right? Gas and pyroclastics erupted from the crater. It was very explosive, so it is relatively sour in composition, acidic, felsic. And then you have some lava that was breaking out at the base of these cones. Maybe not that acidic. And this is a kind of the contradiction that we're seeing here in this area. Right? Cone flanks, they are typically steep dipping 30 degrees, and you try to walk or run up a 30-degree dipping cone flank, and you know that won't be very easy. Okay, and the source of the magma is kind of uncertain. It was probably a weak spot related to the adjacent crusted Basin and Range area. It is thin crusted, and to the north we have then the transition zone and the Colorado Plateau. And the magma moved through the fault system. And here you see the Sunset Crater, very steep slopes, 33 degrees typically, and this one was dated to have been formed some 1,000 years ago, between 1040 and 1100 years before present. So it's pretty active stuff, right? And here you see a volcanic bomb. I showed them before, at the parking booth of the Flagstaff area near the cinder cone, and that's definitely larger than 6.4 millimeters. Okay. So now the story gets a little bit strange, because you're on the middle of the continent, and when you talk lava flowing on the crust or the surface of the ocean, the crust tends to be acidic, high in quartzes and so on. The ocean floor tends to be more basalt-like, high in dark minerals. So here there's a cinder cone coming down. We're at the base of the cinder cone where lava flowed out onto the surface through fissures, smaller fissures. And if you look here at this lava, you see the cooling texture of the lava. It looks like a series of ropes. And that type of lava identified especially in Hawaii is called there pahuhu. Pahoi. I'm not that good in whatever they speak on Hawaii. Here you see a close-up of that rope-like texture. Now, low rope-like textures are indicative indicative, as already indicated by the fact that we are using Hawaii nomenclature, right? Low viscosity, it flows easy, is a sign of dark minerals. Acidic stuff is flowing much slower. It has a high viscosity. So we thought we were working with an acidic form of volcanism, and then we get this, right? We also get this stuff here, other Hawaii nomenclature, but this is all small particles glued together. Like this lava is all particularized, little pieces of whatever, right? The size of a coin, a quarter or smaller, right? And this is called aha. But that is more example of more viscous lava, viscous lava, which is tougher and flows slower and is more acidic in nature. So we're getting here contradictions. Well, there is another contradiction here. In the same area, Mount Wilson Mount in Oak Creek, around Sedona, there. Flagstaff, but the Cindercorn was here, right? Jerome was somewhere there, met Mount Mingus, and here in Sedona, we have Mount Wilson, and it has basalt lava flows. How do we know? Well, if you go to Oak Creek Canyon, I continuously seem to make mistakes when recording this shit. Pardon the language. So we're looking here at a geological cross-section that I stole out of some book that I bought in a Sedona shop. And here we have the typical red sandstone-like deposits of Sedona. And there we have the carbonates of the Kebab Formation. And then strangely enough, on top of it, we have this basalt layer of the Mount Wilson basalt. What the heck is a basalt doing here in Oak Creek? We are on a continental setting. We should have acidic volcanism, high with felsic materials, and not something that is as low viscous as a basalt flow. The interpretation is that if this stuff, I'm not quite sure what the age is of this. I suspect that we're somewhere in the Cretaceous, and that this is a Cretaceous carbonate, and that means that the basalt was somewhere 100 million years ago when it happened. And I want to remind you that when you go back to Mount Mingus, that rhyolite succession and the volcanic ash that we saw there was 1.8 billion years old. And the Sunset crater was only 1,000 years ago. So this is probably 100 million years ago. And when we go on the next portion of this course, when we start stratigraphy talk and other nice stuff for a petroleum geologist, then you'll see that I'm just guessing here a little bit, but it is strange, this very complex transition zone area between the Colorado plate and the range and basin to the south of the transition zone. Okay, so here we're looking at the Oak Valley. We're looking, I think, from Sedona. And then here you have the Sedona red colored sandstones, and that may be the Kebab carbonate settings. And then on top of it, we have this weird basalts. And you can see that if you look at this basalt plateau and then bang there, it is a lot lower. So that is probably the Oak Creek fault. And there might be another secondary fault in there where you see the layers drop a little bit on the right compared to the left, right? You see this drop there from the carbonates and then the overlying suddenly thickening basalts. But what is a basalt doing here in the middle of the continent? This should be acidic, not basalt or low acidic or low viscous lava flow. And I can tell you that this is a basalt. Here's a close-up. I risked my life driving up to the road and then to the parking lot, and I'm using my telelens to get the shot, right? So here you see a basalt. And how do I know that it is a basalt? Because basalts have a very typical morphology. When the basalt lava cools off, it cools off and it shrinks and forms these columns surrounded by shrinkage surfaces or fractures, right? And if you look up from above onto one of those columns, they are often six-sided polygons or hexagonal features, right? That makes it very characteristic for basalts. So here you see the basalt columns of the Wilson Mountain basalt, and I didn't invent the name basalt. That were the guys that did the actual mapping here, right? And so we're looking at ocean type of lava flows, or Hawaii type of lava flows, in the middle of a continental centric that should be as sour, as rich in quartz as any magma can be, whether it is a pluton or whether it is a basalt flow. It should be acidic, and it isn't. There's lots of cross contradictions in geology, and I would like to point out that there is still a lot to be solved in this science. And with that, we're moving on. See you at the next episode, and I think that is about stratigraphy.